Have you ever gone into an exam, looked at the first question, and just had no idea where to even begin? That's probably what you're thinking when you look at the paper flight planner. And there's a little more at stake than a simple bad grade. But the good news is all the math that goes into this is super easy, like 5th grade level easy. And this exam is open book. It all boils down to understanding why each section is important and where to find those little bits of information. You can think of yourself as a detective looking for clues to solve a mystery. First, let's talk about the order that I like to solve this problem. We'll be setting up for a maneuver lesson with simple legs, but you can easily apply this to a cross-country flight with minimal tweaking. You can definitely start from top to bottom, left or right, but I like to go in this order because looking things up multiple times in the POH can get a little tedious. Also, I'll throw together a PDF of all this so you can use it as a checklist. I'll also put links for an E6B and a plotter so you can order them from Amazon. Checkpoints. I like to list my departure, top of climb, a visual release point where I plan on beginning my maneuver phase, maneuvers, thinking like an astronaut, a re-entry point, top of descent, and our destination. Keep in mind, I like to plan for a traffic pattern entry 1,000 feet above the field, so we'll tack on a little extra fuel for the pattern and taxi back to the hangar. Altitudes. Pretty simple. We start with field elevation, climb to an initial altitude, return at that same altitude down to pattern altitude. I like to keep my last row as cruise altitude because that's where this leg starts. Winds and temperatures. You can use the METAR for wind direction, velocity, and temperature at the field, and the winds aloft table from your weather brief for the winds at altitude. We'll need this to calculate our wind correction angles, true airspeed, and density altitude. True course. Using a plotter, you can determine the course you want to fly on the chart. I place the center of the plotter where our course intersects a grid line and align the north-south or east-west lines with that grid line, and read the course from the pencil mark. This will be the same course for climb and cruise. And if we're using the same point for our re-entry, we can simply add or subtract 180 degrees from this course for our return legs. We can also use this time to note the VOR bearing we'll be using for redundant navigation. Jot down your frequency, identification, bearing, and whether it will be to or from indication. Airspeeds. Remember that indicated airspeed is the airspeed read off the airspeed indicator, and it's great for controlling the aircraft, but not so great for calculations. We use the calibrated airspeed table in the POH to account for installation error, and if you're in a goofy plane like mine that uses miles per hour, we can convert that to knots using the E6B. Then we can plug the density altitude into the E6B, read the calibrated airspeed in knots on the inner scale, and read the true airspeed on the outer scale. I'll post a separate discussion on determining density altitude, but a good approximation is to subtract the current pressure setting from the standard 29.92, multiply the difference by 1,000, and add that to the field elevation. This is your pressure altitude. Then place the field temperature across from the pressure altitude, and that should give you your density altitude. Our POH gives us our cruise airspeeds in true airspeed, so we only need to convert from miles per hour to knots. Fuel burn and rate of climb. Since we're in this part of the POH, let's just note the fuel burn rate for full power and for cruise power, and note our rate of climb. Wind correction angle. Using the wind side of the E6B, place your grommet on 100, turn the index to your wind direction, and make a pencil mark for our wind velocity. Rotate to your desired course, and slide the circular part of the E6B until the pencil mark is on your true airspeed, and read the angular difference and direction from your desired course, and read the ground speed from the grommet. Variation. Add or subtract the magnetic variation between true and magnetic north, and remember that east is least and west is best. Magnetic heading and compass heading. If there is a compass correction card in your aircraft, you can account for the magnetic deviation here. Now we'll repeat for the cruise phases. Wind correction angle. Using the wind side of your E6B, place your grommet at 100, turn the index to your wind direction, and make a pencil mark for your wind velocity. Rotate to your desired course and slide the circular part until the pencil mark is on your true airspeed. Note the angular distance and direction from your course and the ground speed from the grommet. Variation. Add or subtract the angular difference between true and magnetic north, and remember that east is least, west is best. And of course, if there's any deviation in your aircraft, you can note it here. Climb. We subtract our starting altitude from our cruise altitude and divide the difference by our rate of climb to determine a time to climb. This is in minutes. Convert this into hours by dividing by 60 minutes per hour. Distance to climb. Now that we have a time in units of hours and a velocity in units of nautical miles per hour, we can determine a distance for that climb. Fuel burn for the climb. Using a rate of gallons per hour and our time in hours, we can determine the amount of fuel that we use for this leg. I like to add an additional gallon of fuel for our taxi and run-up. Note that some POHs will tell you your fuel to climb and include a taxi and run-up built into that number. Cruise. Distance for cruise. Now that we know how far we will travel during climb, we can make a mark on the chart and determine distance from that point to our release point. Knowing the distance in nautical miles and the velocity in nautical miles per hour, we can determine the time it will take us to travel this distance. Fuel burn for cruise. Using this time, we can also determine the amount of fuel we plan to use for this phase. The maneuver phase. Time and fuel burn. I like to allot a set amount of time and fuel burn for my maneuver phase. And since I will likely be adjusting the power for different maneuvers, I like to just assume that I'll be using full power. I'll be conservative and go with my full power burn rate. So for 30 minutes at full power, in this case, we'll allot 3.3 gallons. Coming home, I like to work backwards, starting with the descent. We'll need to determine the altitude change, the time, distance, and fuel burn. Like before, we take the difference between our starting altitude and our ending altitude and divide it by a rate. In this case, 500 feet per minute is nice and comfortable and makes for some easy math. This gives us a time in minutes. Note it and convert to hours by dividing by 60. We can use this number for distance since we already calculated our ground speed. We can also then use it for calculating our fuel burn. This is where I would add an additional gallon for the pattern and taxiing back to the hangar. Cruise from re-entry to descent. We will need to determine our distance, time, and fuel burn. After noting the top of our descent on the chart, we'll work backwards and determine distance from our re-entry point. Using distance and velocity, we can determine our time for this leg. And using time and a fuel burn rate, we can determine the amount of fuel we plan to burn for this leg. Remember that we legally need an additional 30 minutes of fuel at cruise, so tack it on before you determine total fuel. Add up your total time, total fuel, and distance if you're planning across country, and make sure it looks about right. Now that we have a minimum fuel for this flight, we can flip the page over and do our weight and balance calculation to determine that our plane is not too chunky to fly. You can also use this form for field information and general flight planning. All of these calculations are a form of flight planning called dead reckoning. We use this in addition to pilotage, GPS, and VOR for redundancy in case one of our systems fails. For a better understanding of how VORs work, watch this video here.